Okay, so we were discussing backshift operator, and what we quickly review what we were doing last Tuesday. So we took the detrending, the chicken price, that data set. So we can clearly see the price of the chicken has a strong trend, maybe a linear trend or something. So we considered, okay, xt, which is a price, which is a mu t plus yt. Mu t is the trend and yt is a stationary process most likely. So mu t, you take a simple beta naught plus beta 1 times t trend, and we fit a model, and then after fitting the model, you at each time point you estimate the fitted values and subtract it from the observed values. That will give you the residual process, and this is the residual process essentially, which is a mean stationary process. Okay, so this is what we discussed, and then if you take the correlation, autocorrelation function clearly says that what you seeing that the mean stationary process does have some autocorrelation structure. So you can use now some kind of ARMA type model to model the mean stationary residual process, also known as the detrended process. Alternate method was, you take, instead of go through the route of detrending, you take the consecutive difference of the process. So you just take the price, take the consecutive difference, that is your first difference, and first difference turns out to be mean stationary process itself. So then we look into the autocorrelation function of the first difference, and turns out that it is a highly sinusoidal behavior. So this is something very interesting what we found, right? So then we discussed that, okay, differencing, either you can take the route of differencing technique, or you can fit a trend line, fit a seasonality, all these things, detrend your line, your method, and then after detrending you take the residual, and on the residual you do a forecasting model. So this method of detrending and then forecast is slightly popular in the industry, because what happens that if you fit a trend line and a seasonality line, it takes care of the long-term trend. And ARMA models, they are very good at forecasting the short-term forecasting. So your model is inherently taking care of the both trend and for short-term forecasting accuracy. On the contrary, if you use the first difference technique, it will also, you can see that it will also take care of the if you correctly do that, particularly if you can correctly fit the SARIMA, that it should be able to pick up the trend part and the seasonality also. But if you miss it, then you will miss it very badly. So in first differencing technique, you should have very strong idea about what is your periodicity, major fundamental periodicity. If you miss that periodicity, what is your fundamental period, then there is a good chance that your ARIMA model or SARIMA model will be very bad, will give you a very bad forecast. And we will do a exercise where we purposefully choose a bad frequency, and you can see that the forecast is going everywhere, and it will indicate that in case you miss the fundamental frequency, means to capture the fundamental frequency, then it may go very wrong. So that is one of the reason people try to do a slightly risk-free strategy, is for sure you do a trend modeling, and for sure you do a seasonality modeling, and then try to build on the top of the process. So this is I personally feel detrending technique is slightly risk averse technique, but both methods are equally strong, equally good. Both technique, there is no this is the way you have to do or no that is the way you have to do. You can try both. That's my point. Also in the detrending process is also popular in industry because you have the explainability part, that okay, this part of my model is talking about trend, or that much is talking about trend, or this part of the model is because of the seasonality, or this part is because of the local structure or local whatever locally happening. So those things you can clearly tell in your model and all. Whereas if you look into the ARIMA model, when we will see the original mathematical construct of the ARIMA model, we will see that ARIMA model is slightly, I mean, every term is explainable, but slightly in a black box in nature. You cannot really say, okay, this part is because of the trend and this part is seasonality. So differencing versus detrending. So here we took the differencing of the xt minus xt minus 1, and then we did that, we figure out okay, beta naught is gone, the base parameter is gone, beta 1 as a function of yt minus 1. So that's what we found. Then we introduced a Nabla operator, or there was a mistake last lecture. Here I called this Nabla as the backshift, but actually it is a difference operator. Difference operator is basically consecutive differences of my series. And this is also called the first difference. Okay, and the first difference, first difference eliminate the linear trend, second difference will eliminate any quadratic trend, and all these things will happen. And backshift operator is nothing but, you can also known as the lag operator, is bxt is just xt minus 1. So b2xt will be just b of xt, b of xt now is xt minus 1, and b of xt minus 1 is, if you just take the definition, it becomes a xt minus 2. So b2xt will give you lag 2 operator, lag 2 value. Okay, so bkxt will give you lag k value, or xt minus k. Okay, so this is and then typical algebra works in perfectly well. A b inverse b will give you 1, xt equal to b inverse bxt is, you can write it in that way, b inverse xt minus 1, because b of xt is xt minus 1. So that means b inverse is called forward operator, forward shift operator, or forward operator. Okay, so if you want to xt and you want to do a forecast, during the forecast this operator will be useful.
In the difference operator, where you were talking about that quadratic trend, to eliminate the quadratic trend, we need the second difference first difference and next difference. While handling a data, suppose I am doing the first difference and then doing a build. How do I see the
Plot it.
But the second difference, like the trend is quoted.
You have to plot. You have to plot it and then check. You take the plot. You take the first difference, plot it. If it was first difference, and if the trend is got eliminated, then you will see that it is stationary. But if it is a quadratic trend, so that means it will behave like this, right? A quadratic trend will behave like this. In that case, what will happen, after taking the first operator, it will be like this, then it will look like this, more like a parabola. just the trend got eliminated, but the quadratic behavior is still there. So what was looking like this, now it will just shift it, like just angular shift had happened. It will behave like a parabola. At that time, what you do is you have to plot, and you can get a sense, and then you can do a second difference operation. Yeah. So, and then you can first difference operator as xt minus 1, xt minus 1 you can write it as a b of xt, and then you take xt common 1, and that will give you 1 minus b. So the nabla is basically analogous to 1 minus b. And then same way you can write, then this is the first difference operator. Now the second difference operator is second difference nabla 2 xt, you can write it as a 1 minus b whole square of xt, and now you can apply your algebra, which will give you 1 minus 2b plus b square, and now remove the parenthesis. What you get at the end, xt2 minus 2xt minus 1 plus xt minus 2. Okay, so this will give you lots of permutation combinations, and it will help you to explore lot of different models without much of a difficulty. So this is that is one of the advantage of these operators, backshift operators and the difference operator. So all right, now if you raise it to the power d, then essentially you can just expand it to the d terms, and then you can apply xt and you will get the whole thing. Okay, so all the algebra that you have learned in your bachelor first year, second year will just go through in this case. First difference, all right, now the first difference is an example of linear filter applied to eliminate the trend. So you can call it as a linear filter. The second difference, sometimes you can call it as a quadratic filter. So if you apply second difference, it will you can call it a quadratic filter to eliminate the quadratic effect. So this way you can think of. Now the other filters formed by an averaging values of near xt produce adjusted series that eliminate the other kind of unwanted fluctuations. So basically these are the main thing, and difference technique is actually extremely important component of the ARIMA model. Okay, so for example, let us take this global temperature data set from the book, and it looks like it is behave like a stationary process, random walk process, not station, sorry. It looks like it behaves like a random walk process, almost. It could be a random walk process. So what you do, you just take the first difference. Okay, if you just take the def of the globe temperature in this one line and plot it. It looks like a complete mean stationary process. So it could be all it was effectively it was already a residual process, increasing trend residual process. And the question was, other than trend, is there anything else? If there is nothing else, then other than trend part, everything else is a white noise, which will behave like a random walk. What is random walk? Cumulative sums. So you are just doing a cumulative sums. So other than trend, so random walk is mu. Remember the drift plus that cumulative sums, that what we thought. So maybe there is a drift term. After the drift, everything is cumulative sum of the white noise. So here is the drift part. This is the positive drift part, and then everything looks like a white noise. But is it really white noise? So let us look into the autocorrelation function. So autocorrelation functions, this is the first one is obviously 1 because it is with itself. Then the 1 is very close to something, second, third, fourth is something, and then rest of them are mostly like, very close to, it's very weak. The correlation is there, is very weak. It is a 2 standard deviation, and we barely these things are crossing your critical level, and you are doing like in out of so many lags. So most likely these are all white noise. You don't have enough signal. So it was basically just a trend and some white noise along the trend. Okay. Now fractional differencing. Now the fun part is, when we talk about the differencing, we always think differencing in terms of integer, like first difference, second difference, third difference, right? The funny part is, because you can write your differencing in this kind of format and you can apply your algebra, you don't have to really take your d exactly integer. You can take your d a fraction. Okay, I understand it is like a bit of a abstract idea, but it is actually doable. You can think about it, that whether you can do it or not. The answer is, all you have to do, just think about it. If instead of 1, can I take half here and then expand it, it will give me a model, raised to a model, right? So very popular approach nowadays in the time series is fractional ARIMA models, which is slightly beyond the course structure. At the end of the syllabus, if I have time, I will try to do something, but I'm just giving you a horizon that okay, these are the kind of models which are beyond your master's class, beyond almost at the research level, PhD level work. So you can take these practices of fractional ARIMA model in industry. In industry also, actually now they have started adopting fractional ARIMA model. It's not like they are not using. Obviously not very, it is not rampant. Okay, not very people actually know about it, but you can take these practices out there in the industry. Now, why fractional ARIMA turns out to be very popular? Because it has been found that this fractional differencing captures certain interesting phenomena. When this fraction d is between 0 and 0.5, it is known that the series contains some long memory process. Certain memory in the the correlation, autocorrelation is long, very long, and so if you can capture that autocorrelation, you can take certain advantage of building a slightly accurate model, because that is turns out to be inherent nature of the structure. It is not completely white noise. Even within the, so there is a Brownian motion you have heard, like white noise. Basically, there is, when you take the white noise variables, if you assume all these random variables are Gaussian, then resulting process is typically known as the Brownian motion. Okay. The problem is in the Brownian motion structure, it is completely white noise. You cannot predict anything, and any two consecutive will be uncorrelated. The correlation will be 0. And then a version of Brownian motion came up, which is called fractional Brownian motion. And they will have some correlation. They will behave, if you just look into the path, the plot of the series, it will behave like, it will feel like, it is a Brownian motion. It is simulated from a Brownian motion, but it has some inherent correlation structure. So those things, so that is one of the reason. And if you know that your process, even if it behaves like almost like a Brownian motion or white noise, but still it has some inherent correlation structure, so that means you can use that correlation structure to forecast slightly better than Brownian motion.
In case of backship operator, we have the time series observation belonging to the at those elements. So we have xt, y, x, and so x1, x2, and so on. So if I have that d is equal to 0.5, then I have a gauge.
So when you are doing a backshift, you have to think about t as a continuum. On that you have to apply. So it's slightly difficult because the whole thing goes into the continuum. So that's why I said that I'm just giving you a reason why fractional ARIMA, fractional models, time series models of ARIMA models, fractional Brownian motions, all these things are getting very popular, or at least definitely in academia and some quant groups of banking industry. But and it is slightly in a niche, but these are the really state-of-the-art things that you guys can take it out to the industry. That's my point. So, but it is definitely not in the part of this curriculum. So, some of the transformations that you have to work on, probably definitely one is the log xt that you know, and or Box-Cox transformation. These are also, you can try to see if that gives you a sort of a mean stationary process, or at least this kind of transformation definitely helps you at variance stationarity. That for sure. So here is one more example, paleoclimatic glacial waves. So melting glaciers deposit yearly layers of sand and silt during the spring melting season, which can be reconstructed yearly over a period ranging from the time of deglaciation began in New England about 12,000 years back, and it ended about 6,000 years ago. So just looking at the glacial behavior, I don't understand the science, so they have something. And now such sedimentary deposit called verves can be used as a proxies for paleoclimatic parameters. That some of the paleoclimatic parameters such as temperature, because in warm years more sand and silt are deposited from the receding glacier. Okay, So if you look into this series, this is the verb series. Initially, basically, you can see there were not much, but then there was a sudden jumps in some of the years. Now if you take the log transformation, you can see that at least what is happening, that the volatility now has a defined band. Of course it has its own trend and thing kind like that, but it's not mean stationary for sure. It is hovering over a mean, but its volatility band has now a sort of a kind of stabilized. So this helps when your variability. So if you can now think of, if you have a sort of a, if you can fit a nonlinear trend line and subtract that nonlinear trend line, then all these values will become a mean stationary process. Okay, so fitting a nonlinear trend line is very useful on the data, because once you have the nonlinear trend line in this kind of data, then you just subtract basically d trend and residual become a nice mean stationary process, and then you apply your ARMA, anything, all these things. Now in this kind of scientific analysis, forecasting is not an issue. You don't want to forecast or anything. Most of the time what people do in this kind of thing, they want to just understand the science and understand the how the world used to look like in those years. 10,000 years back or 8,000 years back, how world would look like, used to look like. They want to study those parameters based on. So here more like you have to focus on the analysis part of it rather than trying to really build a forecast model. So oftentimes, as I said, the time series analysis is also, this is a tool. End of the day, it is a tool. So you have to understand the context in which you are applying these tools. So okay, I'll just take a pause here. So previously we discussed the filtering or smoothing a time series or moving average to smooth a white noise, right? So this method is useful in discovering certain traits in a time series, such as long-term trend, seasonal component and all those things, because it's so. If you look into the ARIMA, it has effectively two models, autoregressive model and moving average model, and then you integrate them. So first we will start with understanding the moving average and how can we generalize, and then we will start with the autoregressive, and then we will go to the integration of the two. So the moving average, it represent, you can think of it as effectively weighted sum of the k consecutive observations, or 2k. What I have taken j from minus k to k. So you take t, right, and k plus 1, 2k plus 1 actually, because if I take t on the right side, I will take k observation, on the left side I'll take k observation. So t minus k to tk, t plus k. So t minus k to 0 is k observation, 0 is 1 observation, and then rest of the k observations. So 2k plus 1 observations. So if you take k equal to 1, then you are using 3 observation, just window of 1. If you take k equal to 2, you are taking window of 2, and your number of observation is 5. If you take k equal to 3, then you are taking a window of 3 and number of observation is 7. Okay. Now question is, obviously one thing we would like, you have to make sure this AJ, which is a weight effectively, should sum up to 1. Okay, otherwise so basically it should be a weighted mean. Generally you can take 1 over 2k plus 1, that will work, that will be simple. AJ could be 1 over 2k plus 1, that will give you the simple mean. But not necessarily you have to take always 1 over 2k plus 1. If you want, you can give a slightly less weight to the one which are further and slightly more weight to the one which are closer to the tth time point, so that you get a much more meaningful mean. So here consider the monthly SOI series with weights A0 like 5, k equal to 6, then plus minus thing, and that will be 1 over 12. Okay, 1 over 12, and A plus minus 6 itself is 1 over 12. So this particular method removes or filter out the obvious annual temperature cycle and helps emphasize the El Nino cycle. Okay. So here is the plot. Okay. So this, if you just look into this, so there is a natural annual cycle. Okay. And then you apply this filter, which is called boxcar filter, which is nothing but this guy. Okay. And that gives you a sense of how the El Nino cycle were working. So El Nino cycle is about 5 to 6 years of period. So 1970 and 1980, if you look into that, between that you have 2 to 3 cycles. So typically 4 or 5 years you will see some kind of cycling behavior. Okay. Now you take that El Nino cycle and you can use El Nino series. If you believe that this smoother series is giving you a sense of the El Nino, when the overall system becomes much more warmer, use that series to see how it is affecting the recruitment or the ecodiversity, the fish diversity of the population, and might be all you know, that will be much more useful information. Okay. Now I am generalizing that and bringing the idea of something called kernel smoothing. Now instead of AJ, I can write, that is a weight, I can write WIT, I transform onto N, you decide whatever your N, XI, and then WIT is basically KT minus I divided by P, some weight, and then normalize that. So you get WIT, get a normalized weight. Sum up to, if you sum up the WI, it will give you 1. Now once you get the T minus I divided by B, B is a parameter. For the time being, suppose we know the value of B. Now once you get the value of T minus I by B, you plug it in here, which is called Gaussian kernel. you will get a some value kz, it's a density value effectively, and then you normalize, use that density value to normalize. Now that one is an interesting, because if you look into it, if your I is close to t, that means the observation is close to t, right? Then this is 0. At 0 we know the Gaussian density is maximum, and if t minus I is large, it is far from 0, and we know that Gaussian density will take less value when it is far from 0. So this is how the filter will looks like, the weight, and this will give you the much more smoother function. So here you have a little bit of jitteriness, but kernel smoother is much more smooth function than, because in the boxcar you have this breaks, this discontinuity in the weight. Because of this discontinuity, you have these, you can see there are some, lot of jittery is still left there. Whereas here it is much more, weight is much more smooth, and that smoothness is bringing you a nice smooth curve. Obviously B will play a role how smooth it will be. B is the band, okay, how much band or weight you want to give it. B will be just basically a sigma kind of role it will play. Then another approach is called splines. So I'm taking a little detour, okay, but I think this is a very useful technique before we really jump into the ARMA, because these spline techniques or smoothing techniques, they are effectively coming all from the moving average technique, and moving average is effectively the pillar bone of, you can call it, the entire ARMA model. So in the ARMA, moving average part tries to capture the inherent trend line in the data. So whatever non-linear trend, so you can see simple moving average, weighted moving average, kernel smoother, spline, these are all effectively generalized version of the moving average, right? Now, so naturally when we will do a ARMA type model or ARIMA type model, the moving average part, so we can see that these guys are trying to pick up the natural trend in the data. Okay, and trend as well as the seasonality, the overall trend in the data. So moving average part of my ARMA model will try to pick up the natural trend of the data. All right, so spline, what it does, if you take again xt equal to mt plus wt, so mt is suppose a quadratic curve t. Now you fit mt via OLS. Now what you can think of, instead of, you cut the entire data time point into k naughts or k beans. You can think of k beans, and once you get these knots, in each of these knots you fit a cubic polynomial, and then essentially what it does a smoothing spline, then it try to minimize these. This is the sum of squares of error, and then it puts up effectively a penalty term, which is nothing but take the double derivative, square it, and then integrate with respect to t. Most of the time you will get a closed form. I think it does have a closed form formally, and then you just run it through optimization, quadratic optimization process, constraint quadratic optimization process. It will give you the smooth spline. So why this penalty helps you? Because m double dash t gives you instantaneous acceleration. At a time point t, what is the acceleration? It tries to capture the acceleration in the system at that time point. So if it is m double dash t is 0, that means it's a flat. But if it is very high, that means that it's going up or down or something like this happening. So obviously, if it is very high, a lot of things are happening. It's like a roller coaster, because sometimes it's going up, going down. So naturally acceleration will be very high. So accordingly, that thing will get captured in your model. Now lambda is going to play also a role as a tuning parameter. If lambda equal to 0, then you don't care how choppy the ride is, and basically you just take mt equal to xt, so which is useless, okay, and the ride would be completely rough, so it will be like really. On the other hand, if you put lambda very, very large, so we insist on no acceleration. In this case, you will have a constant velocity, and it will be just too smooth. There will be almost like no acceleration will be taken, like no ride and all these things, just a constant velocity. It will just go like that, and it will be too smooth. So the lambda is seen as the trade-off between linear regression, completely smooth, everything is smooth, just a straight line, and the data itself completely rough, like going up and down, up and down, up and down. So somewhere it tries to bring it to somewhere in the middle and try to capture the trend line. So the fitted spline line is something like this, which I think much better. Okay. Now you don't have to always use spline as a function of time. You can model it as a function of another variable also. Here I fitted a spline where mortality is a function of temperature. Okay, so instead of t, I just took the temperature. Instead of time, I just take the temperature, and it will go through. It is end of the day. Again, these are all tools. Remember that. How you use that tools, it's up to you. So now I think we are ready. We will jump into the general technique of the moving average, and we are ready to start the ARIMA. So let us ARIMA models. What happens is, in the classical regression, it is not enough for explaining all of the interesting dynamics of the time series. That we have seen, and we have understood that it has its own limitations. the ACF of residuals of simple linear regression fit of the price chicken reveals that additional structure in the data regression did not capture. So if you remember, in the chicken price data set, when we took the residuals and we fit the ACF plot, so there was definitely lot of autocorrelation structure which was completely missing, which if we just build a simple train type model with maybe some Fourier transformation as a feature engineering kind of thing we put in and develop a model like that, the problem is we do not just simple regression is not enough to capture those autoregressive structure in the covariance part. Okay. So because remember that in the simple regression model, what we are assuming, we are always assuming epsilon is normal 0 sigma square I, means covariance between the epsilon I and the epsilon j is 0. We are always assuming that. An ACF plot saying us, no boss, your residuals are actually correlated. If the residuals are actually correlated, you are leaving a huge information out by making a very strong assumption that your residuals are independent or your residuals are not correlated. So in your analysis and your model should capture the correlation structure, if there is any, in the residual. So here is the idea for that I had that real data, the main data. If you fit a trend, after detrending I got this data, so if you remember, and then I fit the ACF plot on these detrended data. So this was my ACF plot. So that trained model did not capture this autocorrelation structure. Simple trained model will not do that. And my residual plot looks like it is may not be even normal. Okay. So if you remember the autoregression model, autoregression models are based on the idea that the current value of the series xt can be explained by the function of the past p values of the series. So xt will be function of xt minus 1, xt minus 2, xt minus p. Now if you remember, if this model xt equal to xt minus 1 minus 0.9 xt minus 2 plus omega t, where omega t is Gaussian with variance 1. Okay. Now if I have to do a forecasting of such a model, then n plus 1th term will be simple xn minus 0.9 xn minus 1, but the quantity of the forecast at next n plus 1 period will be based on the observed x1, x2, xn. So based on the x1, x2, xn, I am going to forecast the xn plus 1. So I can use these model to forecast the xn plus 1. So the extent of which it might be possible to forecast a real data series from its own past value can be addressed by looking at two things. One is the autocorrelation function, another is the lagged scatter plot matrices. So I can just take the lagged scatter plots, look into it, that could be a interesting thing, or I can look into the autocorrelation function, and from the autocorrelation function we try to make sense out of it, that whether which major lag we should consider in our model. So if you remember, so this was the autocorrelation function. This is a standard autocorrelation function, and here is the, I can plot a Southern Oscillation Index and lag 12 Southern Oscillation Index, and they are positively correlated. Okay. So either you can look into the lag scatter plot, or you can look into the ACF, and from the ACF plot or from the lag plot you try to figure out which of the lag you should definitely consider in your analysis. Okay, so before we jump into the model and anything, do you have any question? The strategy that I generally take is you first look into the ACF plot and the PACF plot, and then you see that other than the lag 0, like lag 0 doesn't make much sense, which is the major lag where you see a real spike in the correlation. Suppose this is a lag of, I don't know, 10 or 15 or some lag, 15 lag. Okay, then you look into the scatter plot of lag 15 versus the current value, and do you really see a very strong pattern? Okay, so this is what typically I do. So it's like not only ACF is telling me that there are possible lag, also the data itself should tell me the thing. So take the actual series and take that major lag, because if you have say 40 lags, right, for each lag if you create a scatter plot, it will create 40 scatter plots, and looking through all 40 scatter plots, it is very difficult to make any sense out of it, right? So what you can do instead of that, you just choose look into the ACF plot, identify which lag value you have a very, like for here, if I have to see, like, all right, it looks like maybe here there is a plot, there is a very strong correlation. Then I look into what lag that is. It may be lag 1, which is the annual lag, and then you take lag 12 scatter plot, and looks like makes sense that annual scatter plot will be highly correlated. Is that answer your question?